Hello everyone, in this video Louis Romain and I are going to present to you the project of the smart control of traffic light using AI. For many years, the traffic light increased the big cities and becoming a problem. Traffic jam cause fuel consumption and air pollution. It is so important to find solutions to reduce pollution. In fact, there are already some. The old one is manual controlling, traffic controlled by policemen. It is okay for small area, but it is a disadvantage in megacities because humans cannot see everywhere. Traffic lights with timer is the most used in the world. It is simple, however, it is not adapted according to the real time. Electronic sensor, less used than others, it is a new technology that detects traffic and collect data on the road. It is very interesting method, but is an expensive technology. The smart control of traffic light using AI is a promising solution.
Now, let's see an overview of the system. So, the proposed system uses CCTV cameras from the traffic junction to calculate the traffic density by image processing and object detection. For the software, we are using the software YOLO, which means you only look once, to detect the number of vehicles of each class, such as cars, bikes, buses, trucks. For the traffic light management, the traffic density is used to calculate the signal switching time. It uses some other factor too to set the green signal timer for each lane. The red signal times are updated accordingly. To avoid starvation for a particular line, the green signal is restricted to a maximum and minimum value. For the description of YOLO, YOLO is a clever convolutional neural network for performing object detection in real time. The algorithm applies a single neural network to the full image and then divides the images into regions and predicts bounding boxes. YOLO is a very popular software because it achieves high accuracy while also being able to run in real time. So here is the result of the algorithm. For the signal detection, the algorithm takes info about vehicles that were detected from the detection modules and use as an input to calculate the total number of vehicles of each class. Then the grid signal time is calculated and assigned to it, and the red signal times of other signals are adjusted accordingly. There's many factors that we're considering with the developing of the algorithm, such as the number of lanes, the total count of vehicles of each class, the traffic density, or also the time added due to lag of each vehicle. When the green light timer reaches 5 seconds, the detection module takes a snapshot of the next direction. This gives the system a total of 10 seconds to process the image, to detect the number of vehicles of each class present in the image, to calculate the green signal time, and to set the times of the other signals accordingly to the green signal. And here it is, the formula to calculate the green signal. So as you can see, GST is the green signal time. The number of vehicle is the number of vehicle of each class of vehicle at the signal as detected by the vehicle detection module. The average time of class is the average time the vehicle of that class is taken to cross an intersection. And the number of lanes is the number of lanes at the intersection.
Upon training, the AI reaches a real-time detection accuracy of 80%. This means 80% of the traffic density has been correctly detected and identified in the right category. This may seem insufficient, but this is due to a lack of proper dataset. In fact, real-life footage from traffic cameras should be used to properly train the model and reach a near-perfect vehicle detection. In spite of these poor scores, the algorithm has been tested and compared to an existing static system through simulation. From the Figure 3 setup, 15 cases were implemented where each 4 lanes had different traffic scenarios. The objective here is to evaluate the performance of the program through different distribution or level of randomness in order to approach an everyday life use of the AI. Performance is measured in terms of the number of vehicles that were able to pass the intersection per unit of time. The results obtained were tabulated as follows. On the left is a table for the static system and on the right for the proposed system. For all cases, the AI performed better. There is a few cases where the static system did a little bit better in some lane, but the difference is minor as the proposed system was still able to let more car pass through the intersection. Overall, all simulation taken into consideration, the algorithm increased the performance by 23% compared to the current system. We can notice that the more skewed the distribution of the traffic is, the bigger the gap in performance. To sum up, the results speak for themselves. The system can drastically reduce traffic jam and thus reduce fuel consumption, air pollution, extra delays, and so on. This simple setup can easily be adapted to CCTV cameras at low cost compared to other systems. Its use can even be extended with multiple functionalities such as synchronization of algorithms between multiple intersections in order to get even better performances, accident detection, adapting traffic for emergency vehicles, or even identification of vehicles violating traffic rules.